as I mentioned when I was passing this out, we're going to be talking about logic. Actually, let me pull that screen down so my glare goes away. Stop those side conversations, please, so we can get through these. All right. So unit 2 is logic. Okay, this first section that we're going to talk about, we're going to talk about Euclidean, that's how you say that word, Euclidean geometry and inductive reasoning. So I think I actually mentioned Euclidean geometry at the very beginning of unit 1 when we started with our vocab and we talked about points, lines, and planes. Okay, in Euclidean geometry, points, lines, and planes were your 3 undefined terms. Do y'all remember talking about that? They had no size, no shape. They were really just describing them, not defining them, because they are undefined terms. So in Euclidean geometry, things are organized in a certain way. So the basics are those undefined terms, okay? Then we have defined terms. Then we have postulates and then theorems. Okay, you are going to need to know this order. So Euclidean geometry starts with undefined terms, defined terms, postulates, and theorems. We're going to talk about what all those mean. So undefined terms, as we mentioned back in unit 1 when we learned about definition, okay? The ones that we talked about were points, line, and plane. Those are our 3 undefined terms. Okay, now defined terms, those are terms that have a formal definition and can be defined using other geometric terms. Okay, so for instance, a ray or a segment, we defined those using point and line. Okay, things like collinear or coplanar, we defined using line and plane. Okay, so those are undefined terms, are point, line, plane. Okay, and then there are defined terms. Now a postulate, okay, if you haven't heard that word, the postulate, and actually you've heard the word, you've seen it in our notes. Last unit we talked about the angle addition postulate. I don't know if you remember seeing that, but a postulate is something that does not require proof. It doesn't require proof. It is presumed to be true. Okay. So a postulate is, it does not require proof. It is presumed to be true. A theorem, on the other hand, a theorem is a statement that requires proof. Okay, statements that require proof using logic and reasoning. Okay, so that, all that right there above that red line, that's everything about Euclidean geometry that you need to know. Okay, you will be asked what these things are. You need to understand what is a postulate, what is a theorem. Okay, you need to know the organization of Euclidean geometry, the order of undefined terms, defined terms, postulates, and then theorems. So you need to know that order, okay, and the difference between postulate and theorem. Okay, everybody good with that? All right, so now theorems use logic, okay, and unit 2 is all about logic and reasoning. So the first type of reasoning we're going to talk about is inductive reasoning. Okay, so inductive reasoning is reasoning that a statement is true because specific cases are true. Okay, so it's the way that you think or reason. Okay, inductive reasoning is going through this process in your head. You're like, okay, I think that this is true because these examples or these other cases are true. Okay, so when several examples form a pattern, and you believe the pattern will continue, then you are applying inductive reasoning. So pattern recognition, okay, is inductive reasoning. Figuring out the next term or whatever it is in a pattern, okay, you're using inductive reasoning. You're assuming what's going to be next based on the pattern that you've seen. Okay, so inductive reasoning, okay, you use because specific cases are true, okay, you reason that something must be true. Okay, all right, so in this next part, we're going to try to use inductive reasoning to complete or continue a pattern. Oh, I already filled that part in. Okay, you don't have to fill it in again. Okay, I'll put it here again, but you already wrote this. So we're going to continue the pattern using inductive reasoning. All right, so in this first list, it's days of the week. It's Sunday, Tuesday, Thursday. What do you think is going to come next? Do you recognize a pattern? Saturday. Why Saturday? Yeah, so they're skipping a day, aren't they? Okay, Sunday, and then they skipped Monday, and then they listed Tuesday, and then they skipped Wednesday, and then they listed Thursday. So we'd skip Friday, and then we'd list Saturday. Okay, so Saturday would be the next term in the pattern. Now I'm going to put in parentheses after the term why we chose that. What's the pattern that we are recognizing? So I'm going to put skip a day. Or every other day. However you want to word that, put why we put Saturday. Okay, the next is a pattern of numbers. 3, 6, 9, 12, 15. 18. Why do you think 18? Okay, you've recognized the pattern is plus 3, plus 3, plus 3, plus 3. Do y'all see that? Okay, so 18 would be the next term. Okay, because we keep adding 3 or count by 3s. Okay, these arrows. Okay, we have one pointing west or left. Okay, one pointing like up and to the left. Okay, northwest, north, northeast. What do you think is going to be next? Ava? Pointing to the right or east, however you want to think of it. Okay, why? What's the pattern that you recognize? Clockwise. Yeah, it's rotating clockwise 45 degrees. Okay, do y'all see that? So you can just put rotation clockwise. These are hard to see. I don't know if you can see them well on your paper, but it's like little clocks. Okay, I don't know if you can tell where the hands are. Okay, but this first one, okay, it's pointed where like the 1 would be, and then this one is over a little bit, and then a little bit more. Can y'all see the hands on yours? I don't know how well it copied, no. But essentially the hour hand is pointing at 1, 2, 3, 4. So where would it point in the next one? 5. Okay, so I'm going to draw this. Okay, the minute hands are all pointing up at 12, so that's not going to change. Okay, but that hour hand would be pointing down here at 5. Okay, if you need to make a little side note of that and say that that's pointing at 1, 2, 3, 4, 5, you can make a little note of that. Okay. All right, this next one is numbers again. We've got 0.4, 0.04, 0.004, 0.0004. What can we induce? Okay, we're using inductive reasoning, so we are inducing something. What would you induce that would come next?
0.00004.
Yeah, it looks like they're just adding another 0. They're pushing the 4 back in the place value, right? So that has 3 zeros after the decimal before the 4. So this one should have 4 zeros after the decimal before the 4. Okay. I didn't put anything. I'll put 5 o'clock. Okay. Okay, so that's the pattern we're recognizing. All right, now this one is not just letters. I know this one's hard if you are thinking of it just as letters. These are the months: January, February, March, April, May, June. So what would be next? So I'm going to put a J because they are just doing letters. So a J would be next. And the reason is it's the months of the year. But that we're representing July in that one. Okay, and we could continue the pattern past this. We just put the next term, but we could keep going with all of these, couldn't we? Yeah. Okay, this is inductive reasoning, recognizing patterns, okay, assuming what's true based on what was true, okay, in other cases. Okay, so inductive reasoning. Now, a conjecture, okay, so there's still some terminology we need to know here besides inductive reasoning. A conjecture, that is a statement you believe to be true based on your inductive reasoning. So when we were continuing these patterns up here, these statements, or I mean, I didn't write a complete statement, but what we were putting in parentheses out here, these were our conjectures, okay? My conjecture in number 1 is that they are listing every other day. Okay, my conjecture in number 2 is that they are counting by 3s. Okay, their pattern is adding 3 each term. Okay, so the conjecture is just the statement you assume to be true based on inductive reasoning. So making a conjecture, okay, we're going to complete these. We're going to make a conjecture. Yes.
Can I go to the?
Yeah. Go ahead. The product of an even number and an odd number is blank. Now, if you don't know this, that's okay. Let's complete the conjecture using inductive reasoning. Let's look at some examples and see if we can recognize a pattern. Okay, so here's some examples of an even number. Remember, even numbers are multiples of 2, and odd numbers. Okay, so 2 is even, 3 is odd. What is 2 times 3? Is that even or odd? Okay, 2 times 5, that's an even times an odd. What's 2 times 5? Is that even or odd? Okay, 4 is even, 3 is odd. What's 4 times 3? 12, and that is an even number, right? Okay, 4 times 5, that's an even times an odd again. Okay, 4 times 5 is 20. That is also even. So what is the pattern you recognize down here looking at these examples? Even times odd equals an even number. Okay, so my conjecture, to complete this conjecture, I would say the product of an even number and an odd number is even. Okay, I used inductive reasoning. I looked at what's true, okay, and I'm assuming what will continue to be true. I'm recognizing a pattern, okay, and making this conjecture. Does that make sense? All right, last one, making a conjecture. Okay, it says, make a conjecture about the length of male and female whales based on the data. So average whale length, okay, females, and this is in feet for both. Okay, so female and male comparisons. Okay, so what does it look like the pattern is in the comparison of female and male? For the majority of these, it looks like the female whales are longer, doesn't it? Is there one where that's not true? That last one is not, but the majority of them, the female's longer, right? Okay, so I can use that to make a conjecture, okay? I'm going to use what I know to be true based on this data to say that female whales are longer than males. Now, this is a general statement. Is it always 100% true? No, because we can see over here, there's this one instance that it's not, okay? And we're going to talk more about that later, but this is called a counterexample. A counterexample is an example that proves something wrong or not true. Okay, we'll talk more about counterexamples in another section. We won't focus on it today, but just so little preview there. We'll talk about counterexamples later, but for the most part, the female whales are longer than the males. So that's the conjecture that we can make with that data. So far, so good? All right, so I'm going to give you a practice. It is a paper so that you can see and write and draw for some of the patterns I'm asking you to continue. But then I did input it into Delta Math. So you will input your answers in Delta Math so that it grades it for me. And you don't have to turn the paper in, and I don't have to hand grade everything. Okay, but I'm going to give you the paper to do your work on. And then once you finish it, you'll log in to the assignment on Delta Math and input your answers there.